Here's how you write your own machine learning library in vanilla Python in less than 50 lines of code, implementing automatic differentiation using the chain rule and some dynamic programming. Let's go! First we're going to import math and random from the standard library, vanilla Python only. Then we're going to write a class var, which is an extension of the floating point type. It of course contains its value, then its parents building a computation graph, and then the gradient for gradient descent. Then we write a function for backpropagation, which recursively applies the chain rule backwards through the computation tree. We then write the dunder methods for operator overloading, where we return a result var containing the parents, which are the operands and the partial derivatives of those operands. Then a quick update function for applying an update step using the gradient to update the value. Of course, a wrapper function to print it nicely, and then a static method, random, to initialize a random var. And this is it. This is enough. This is machine learning. To see this in action, we create a function to demo the var type on a Taylor polynomial. We define some x input and the true y output. We then define the model, which are some coefficient parameters, which are just vars. Then a function to apply this model. And then of course we want to output the predictions, so we store them. And then we have the training loop, which goes through and calculates the error as a mean squared error and backpropagates on that error value, we call it a loss, with a learning rate. And then of course we update the coefficient parameters. And then we just do this iteratively, however many times it takes for the model to converge. And that's it. This is machine learning training in action. And now for a quick test. We do 100 samples, 2 parameters in the model, 4,000 iterations, a learning rate of 0.001, and then we print out the loss every 200 iterations. Run this bad boy and you should get a figure looking like this. If we plot the model predictions during training, we see it slowly getting closer to the target values. Matrix operations are an essential part of machine learning nowadays, so we're going to implement our own class for this. Is it going to be efficient in Python? Hell no. Are we going to do it anyway? Ooh yeah! A little bit of zero initialization, random initialization, a index getter, an index setter, and apply an element-wise function, which is essentially doing element-wise application of a function on either one matrix or two matrices. Then we use these to do some sweet operator overloading with the dunder methods. Then we top it off with a wrapper method, and then it's of course nice to have a mean squared error loss function to apply onto matrices. To see this in action, we apply this on the most trivial of cases, which is have some examples, then a matrix doing a linear operation and get some true y values. We then have a model, which is another matrix of the same dimensionality as the true matrix. We then pretend we don't know the true matrix, and we try to train the model matrix to perform the same action as the true matrix. Same as before, you have a training loop where you calculate a loss, you backpropagate through that loss, and then you update all the model values. And then you iterate however many times you need. Let's try this on 32 samples, a 3x3 matrix, 100 iterations, a learning rate of 0.5. This should get you this figure showing how the loss is decreasing over time. Let's plot the model predictions over the course of the training. And now comes the fun bit. We pack this in a neat neural layer class. It has weights, bias, activation function. The activation function is often non-linear. This is the secret sauce. We make a forward function to pass along some data. we make an update to update model parameters, then the most common activation functions. To see this in action, we again have some X and Y data. We define a model, which is just a stack of layers. And then the training loop, you know the drill by now. Predict, loss, backpropagate, update, repeat. And this is essentially all you need. Now we have everything in machine learning, at least for neural networks, packed neatly in these scripts. This is what pytorch, keras, tensorflow does. Everything else apart from this is just sprinkles. It's just icing on the cake. This is the bare essentials. This works. It's not efficient. You can go ahead and do this in SIG or C or whatever you choose to do your brain rot in. But this is machine learning and it works. Have fun.